Hi guys, sorry I'm a bit late. So, okay. So, any questions? By the way, I mean the chat is on now, so that's good news. Looks like there are no questions. Okay. So now the last new thing I'll do before we start a kind of review and all that preparation for the upcoming midterm would be this chain rule section on chain rule. So let me do the section on chain rule. Okay, so of course you know chain rule from one variable case, right? This two variable chain rule is more involved, but is in the same spirit. So let me just explain now. So this is chain rule. So I would say, I think this is section 4.5. So what's the issue? So we have a function of two variables. So let me start with an example. So we have, imagine you have a function of two variables like f of x and y. A function of two variables given. And imagine x and y individually are functions of t. So, okay, this is a function of two variables, this is fine, but then there is an extra bit of information that x is equal to x of t, and y is equal to y of t. So these are functions of t, so you can replace x and y by the values here. So then you get a function like f of x and t and y of t. Right? Okay, so this is now a function of one variable all of a sudden, right? Because this was a function of two variables, capital F. Now this is a function of one variable t, right? So let's call this function, for example, so actually I want to call this little f. I'm sorry for, you have to correct your notes. This is f. So let's call this f of t. So this is this capital function f of t. And we want to now take the derivative of f with respect to t. So df dt is equal to what? That's the question. But we want to find the derivative of this guy with respect to t. Okay, so then the chain rule is the following. In this case, chain rule in this case says to compute df dt, I hope yeah, okay, so this is okay. To compute df dt, we have to compute partial derivatives of f with respect to x and with respect to y, and then multiply those results by derivatives of x and y with respect to t. So let me write it like this. So this is partial of f, and this is little f, yes. With respect to x, dx dt, plus partial of f with respect to y, and then dy dt. This is the chain rule that we are going to kind of use in this case, is this rule. Of course, you should ask, you should ask me, you should press me why this is true. This is like I'm teaching like a cookbook kind of, like a chef now. I tell you do this, do that, and then you're final result is going to be good. But you have to demand a proof why this is true. Okay, so well, I won't tell you why this is true. I will tell you a little later. So, but why? That's a very reasonable and absolutely must question. But let us get used to that, and then I'll tell you. I'll give you an idea why this is perhaps true. So here is actually, so is an example. So this is not an example really. So this is theory. So here's an example. Compute df dt if f of t is equal to f of x of t, y of t with, this is not a very interesting question, I mean interesting example honestly, but this is just an example. I want to give you an example. So let me just give you an example. Anyway. So f of x and y equal to sine of x2, y2, x of t equal to e to the t, and y of t equal to log t. For example, just okay. So solution. Well, I mean, we just have to use this stuff in the cloud now, right? This is what we have to use. So, I mean, what do? I mean, we just say, okay, df dt, d cap f dt is equal to df dx, dx dt plus df dy, dy dt. Now, what is df dx? Okay, so derivative of this partial of f with respect to x. This is partial of x2y with respect to x, which is 2xy2, right? Cosine of x2y, y2 rather, and df dy is 2x2y cosine of x2, y2. Now, partials are very easy in this case. So partial of this guy, dx dt, of course, is just e to the t, and dy dt is equal to 1 over t. So we have to sub into everything into this formula right here. So let me just write it here then. So we have df dt d cap f, I mean dt is equal to, well, df dx is this guy, 2x y2 cosine of x2 y2 times dx dt, which is e to the t, plus 2y x2 cosine of x2 y2 times 1 over t, which is df dy. No, sorry, dx dy. Oh, dy dt, I'm sorry, 1 over t. But notice that we are not done yet because this guy still is in terms of x and y. So we have to still change those guys to x and y. Okay, so that's the next step, and that's easy. This is 2, but x is what? X is e to the t. So we get 2 e to the t log t squared cosine of, well, we just put e to the 2t log t squared plus 2, and y is, of course, yt is log t, and then yes, x squared, which is e to the 2t, right? Cosine of yes, cosine of e to the 2t log t squared, right? Oh gosh, I hope I didn't make any mistake. I think I'm afraid I did a mistake somewhere. I forgot to put e to the t here. It's not a mistake, it's just I forgot to put some extra factor, and here is 1 over t. Okay, everything is in terms of t. Everything is in terms of t, and that's okay. Okay, I mean, so the problem is like just practicing. I mean, it's not a very interesting example, really, but most examples actually in this section are like this, actually. They're not much better than this. But the thing is to kind of prepare your brain to work in the right form with this sort of formalism, because the formalism is very interesting. So let me now write down the general one variable case of chain rule. So general one variable chain rule. What do we mean by this? So we mean this. Given, this is given now. Given f of x1, x2, xn. So this is a function of n variables, x1, x2, xn, right? And we know that this x1 is like, is itself, is a function of t. It's like g1 of t, x2 is equal to g2 of t, and xn is equal to gn of t. So each of these independent variables now become functions of one variable t, which is t. So this is the one variable. Reference to one variable is this t here. And the reference to general is that we have got x1, x2, xn. So this is a general function of n variables. Yes?
The 1, 2, and n, are those exponents or are those like numbering?
Oh no, these are labels.
Okay.
So yeah, that's a very good question. For some reason, I don't want to put the labels down. So these are not powers, okay? These are variables, independent variables. So, okay, so I'm glad you asked this question. That is a very good question. Okay, so then you get this function f, cap f of t, like that case, right? And then this is a function f of like, so well, we get g1 of t, right? g2 of t, gn of t. Okay. And our task is to find the derivative of this function with respect to t, because now this is a function of one variable only. Right? So let's find df dt. So then chain rule in this case says the following. Let's see if there are any questions actually. There are no questions. That's good. Okay, right. No, there are no questions. Okay, good. So the chain rule in this case says that, yes, d cap f with respect to t. So what you have to do is this. you take partial derivative of f with respect to all these variables one by one, and then multiply each of them by the derivative of that variable with respect to t. So it's a big sum, I from 1 to n, df. This is, yes, little f, that's good. dxi. And then we put dxi dt. And remember, this xi is itself a function of t, right? So this is, you can just say, well, that's equal to sum I from 1 to n df dxi. Well, this is dgi dt, because xi are just functions of t, which are given by this gi. So you can write it in different forms, but essentially all of them mean the same thing. Right? So that's alternative notation could be this, actually. You can just say, okay, I know that df dt is equal to sum. What's the notation? What's the alternative notation for partial derivative?
F sub x.
Is f sub xi, exactly. I just put f sub xi. And then this is also derivative of this guy with respect to ti. So this is just, I just put dgi. For example, it comes in many different forms, but they all mean the same thing. They all mean the same thing. They all mean the same thing. Okay, good. So now, let me give you an application. So that's now an interesting example. An application of this chain rule to what actually we did before, namely for the tangent plane to a level surface. I said that I won't prove it, but I will prove it later on when we have this result. So let me prove that result. So this is actually a very interesting application of this case of chain rule. So application to tangent planes to level surfaces, right? So do you remember this issue of tangent plane to level surface? So I said that there is a surface given by the equation f of x, y, z equal to 0. So this is the equation of the level surface, f of x, y, z equal to 0. This is the level surface equation. Okay, so it's given by one function of three variables. And we are given a point on the surface, P. So this is given, and also given P equal to x0, y0, y0. So level surface equation, y0, z0, belonging to S. So yes, level surface S equation. So this belongs to S. Okay, so all I'm saying is that you have given a surface like what we discussed. This is point P, and this is the equation of the surface S. This is the equation. This is the surface S, and this is the tangent plane to this surface, right? And we said that the normal line to this surface, what was the equation of the normal line to this surface? Not line, actually normal vector. You remember? Normal vector surface. You remember we wrote down an equation for the normal vector? Yes.
F sub x, f sub y, -1.
And okay, so that was for a -1. That was for, indeed, that's true, but that was for graphs.
Oh yeah, so the f sub x, f sub y, f sub z.
Yeah, this is actually so symmetric in this case. It's just f sub x, f sub y, f sub z. Indeed, f sub x, f sub y, f sub z. But I never gave you a proof why this is true. Why this is the normal line. To the, normal vector to the surface. Normal vector to the surface. Now I can prove that this is indeed a normal vector to the surface by proving that any curve that is on this surface is actually orthogonal to this normal vector. If I prove that, then we are done. So what we are going to show now is that any curve, so let us show any curve on the surface S passing through x0, y0, z0 y0, z0 is in fact orthogonal to this normal line. So my normal line is not very realistic, so I'm going to put okay, is orthogonal to n. Okay, so let's take a curve which is on this surface, right? So proof that how do you write the equation of a curve? It's just x of t, y of t, z of t, right? This is three variables, all depending on a parameter t. So this is like gamma t. This is the equation of your curve, right? This is your curve. But this is not just a random curve in space. This curve is also on the surface. I'm saying it has to be on the surface, and it's passing through this point. So being on the surface means that it satisfies the equation. This makes sense, right? So f of x of t, y of t, and z of t is equal to 0 for all t. That just means it's on the surface. That's the meaning of being on the surface. Okay? Good. Now, because this is equal, so this is a function of t, but I know that on the other hand, this is completely equal to 0. So I can just take derivative of this, and then derivative of this also will be 0. Because if you have a 0 function, you take derivative with respect to t, it's also 0. So then I know that ddt of this quantity f of x of t, y of t, z of t, okay, that's good, is equal to 0. But now I can use, we can use our knowledge of chain rule to compute this. What does chain rule says? Chain rule says, CR, chain rule says that, well, this is equal to, what is it, fx, right, dx dt, plus fy, dy dt, plus fz, dz dt, right? And this is equal to 0. So what does this equation mean? This equation means that, well, what is fx, fy, fz? This is the normal vector here, right? This is the normal vector. So it just means that the normal, so let me write down that equation in kind of very nice form. So this is the inner product of two things, right? So this is equal to fx, fy, fz, I mean dot with dx dt dy dt and dz dt. So we conclude that this is equal to 0, so it means that this normal vector n here is orthogonal to this vector dx dt dy dt dz. But what is that vector? Dx dt dy dt dz dt. What is the importance of that vector? Remember, this was a curve, and well, I mean, this is the velocity vector to the curve, right? This is just the velocity of the curve. So this is the tangent vector to curve, right? That's it. So that's it. So what this shows is that if you pass through this point, the tangent vector to any curve that passes through this point is orthogonal. This is another way of saying that this normal is orthogonal to the curve. That's what we wanted to prove. So that's one very nice application, no-nonsense application of chain rule in one variable, because this kind of completely corroborates what I said before, and I said that let's accept it and I'll prove it later on, because we need indeed this rule to prove. I don't know how your book actually proved this, but maybe it didn't. Maybe they just gave some examples and justified it by examples. I don't know, but certainly cannot be done at that stage. Any questions or comments?
Yeah, I have a question.
Yeah, please.
So, I'm just a bit confused. For level surfaces, can't we have the function f equal any constant instead of just 0?
Yes, that's fine. But then you bring it to the, yes, absolutely. Yeah, you're right. I mean, I know. So excellent question was asked. Usually when I talked about level surfaces, I said the equations is given by f of x equal to c, some constant, right? I mean, we discussed it like that. Indeed, but if you can bring it to the left-hand side, you get f of x, y, z minus c equal to 0. So this is the function I'm calling my new f now. And notice that partial derivative of this and partial derivative of that are the same. Right?
Oh, I see. Yeah, that makes sense. Yeah.
Because c is a constant, and so partial derivatives are indeed the same. So in fact, we are not losing any information by formulating it like this. But you are absolutely correct to ask this question. This is an excellent question, because when I discussed the level surfaces, I said level surface is this function equal to some constant. But now I'm taking as equation of level surface, some function is equal to 0. But that's not more general than this, by changing your function to f minus constant.
Okay, thank you.
Yeah, sure. And in fact, that's what happens, what we do a lot in physics, chemistry, a lot of engineering, a lot of different places. Instead of putting something equal to constant, you put it equal to 0, but by you understand that you can bring the constant to the left-hand side, and then this is as general as you want to be. Good question, excellent. Any other comments or questions? Okay, so now let's go to, before I prove the chain rule in this case even, let's go to two-variable case of chain rule, and then we'll see some more interesting situations. So the two-variable case is kind of more interesting. So this is two-variable chain rule. So here is the general situation. So I mean, it's not as general. So here is, I just say, for example, so this function f of x and y is given. And the following things are also given. I know that x is equal to, so let me call this capital now. So I promise I won't change this capital to anything else. Okay, so now let's assume x is equal to itself the function of two variables u and v, and y is another function of two variables u and v. So when you sub in, you get f of x and y is indeed a function of little f of u and v and little g of u and v, right? So all of a sudden, this function, which used to be a function of x and y, now is a function of new variables u and v. So we have replaced independent variables x and y by these two new variables u and v. Actually, I have to draw some pictures here so that you see geometrically what is going on. I'll do that soon, but let me just give you the formula. So chain rule in this case is the following. It says that if you want to compute partial derivative of this with respect to u, for example, because we know that after all, this is a function of u and v now. So imagine you want to take partial derivative with respect to u. It just says compute partial derivative with respect to x, and then partial of x with respect to u, plus partial of f with respect to y, and then partial of y with respect to u. And also partial of f with respect to v is equal to partial of f with respect to x, partial x with respect to v, plus partial f with respect to y, partial y with respect to v. Now, there is something that you can kind of control yourself that perhaps you haven't made a mistake. What is the control? Do you see a pattern here, for example, for the first one? It's not totally random. Do you see some pattern here and also here? What do you see?
I know I'm kind of stating the obvious, but it's chain rule, but for each variable inside.
Mm-hmm.
So you do chain rule with x and then chain rule with y.
Exactly. So exactly, indeed, just to make sure that you haven't made a mistake, or at least a blatant mistake, would be just cancel. I mean, this is a very wrong thing to do, but just cancel. I believe it pays you off to do wrong things sometimes. Absolutely. So this, what you're left with? You're left with df du, and then you know that you're on good track. Here df du, because you want to have the df du. Okay, you would say df du is equal to 2 times df du, but bear with me, that's okay. So this gives you control so that you haven't made a mistake. Also here is just cancel. You see df/dv. And then you have the rule that df/dv is equal to twice df/dv. So these are strange things with partial derivatives if you do this sort of algebraic kind of mindless simplifications. But these are sometimes pays off, sometimes gets you into some dark abyss. It's going to be hard to get out. I will give you one more example, which is absolutely interesting, and you will be surprised by that example. Maybe next lecture. All right, so that's the check. So, but now I can write it like this: if u is equal to fx xu or dx du. I almost wanted to write xu, but maybe that's too much. Plus fy dy du. And fb is equal to fx dx dv plus fy d by dv. The point is that here is all the way with respect to v, the partials are with respect to v, here partials are with respect to v. Same thing. So example, find so I'm saying that f of x and y equal to x2 plus y2 find where x is equal to r cosine of theta, y is equal to r sine of theta. Find df dr and df d theta. That makes sense, right? Because this f is a function of two variables, x and y, but each of those guys are functions of two variables independently of r and theta, right? And so once you replace, you get a function of r and theta here. So we are asked to find df dr and df d theta. We are asked to do that. So solution. Now, this is a particular situation. It's kind of is rather simple. There's a shortcut here, right? So what is the shortcut? What can we do in order? I'm saying you don't even have to know chain rule to compute this problem. By noticing something, you don't need chain rule at all. What is it that helps us to compute this without? Yeah.
Does it have to do with like cos squared plus sine squared as well?
Yes. This. Indeed, if you replace x and y by these quantities, you get r squared, because r squared cos squared plus r squared sine squared is equal to r squared, right? So f of x and so f of r and theta. So let me just say it like this. Doing it without chain rule. So, well, I mean, as I said, this is a particular case, so that's why we are able to do it without chain rule. F of r and theta is equal to r cosine of theta squared plus r sine of theta squared. That's equal to r squared cos theta squared, right? Plus r squared sine theta squared. So that's equal to r squared. So as a function of r and theta, f is actually independent of theta. That's good. It's just a function of r. So, okay, so then you can compute. So df dr is equal to 2r. So I'm saying, yes, df dr and df d theta is equal to 0. And that solves the problem. But now let us actually, let's imagine that we didn't notice this. We were not able to make this observation. And let's just do it according to chain rule. But that's good because that also gives us a chance to check chain rule access in this case, right? So this we can do. Okay, so alternative method using CR. What's another word for alternatively?
Equivalently? Loosely?
Loosely, I agree. Equivalently is a good alternative.
Also.
In other words.
What's that?
In other words.
In other words, yeah, they're all. Well, in other words, is a bit far.
Like something more elegant.
Yeah, I want something colloquial and elegant. Formal. Okay, so, well, if you find something, let me know. I like to know this. So alternatively, we can just say DFDR using CR. We have DFDR is equal to DFDX, right? DXDR plus DFDY DYDR. Okay, so let's see what we get. DFDX is 2x, and then DXDR is cosine of theta, right? DFDY is 2y, DYDR is sine of theta. But we are not done. We have to replace x by its r theta value, which is r cosine of theta, times cosine of theta, plus 2r sine of theta times sine. So that's equal to 2r, again cos squared theta plus sine squared. But that's equal to 1. Oh, no, 2r. Sorry, this is 1. This is 2r. So that's good because it kind of verifies what we already know. But well, I mean that's not bad. Okay, let's do DFT theta now. This might be more interesting. Why we get 0 DFT theta? Again, this is DFDX, dx d theta plus DFDY, dy d theta. So that's equal to now, well, DFDX is 2x, dx d theta is minus r sine of theta, right? Minus r sine of theta plus 2y dy d theta is r cosine of theta. Okay, so we have to compute just a bit more and then we are home. So that's equal to 2r cosine of theta times minus r sine of theta plus 2r, what was y? Y is equal to r cosine of theta.
Y is r sine
Right. X is
theta. X is
r cosine of theta, that's okay. Yes, y is r sine of 2r. Theta. Good. So we get negative 2r squared sine theta cosine theta plus 2r squared sine theta cosine theta. So they cancel after all, but yeah, I mean, this is kind of longish calculation that we had to do compared to the first one, right? So of course, in this case was exceptional because using chain rule, actually, we didn't get any dividends by applying chain rule. We just made our life more difficult. But this was a very special situation because that function is just the square of the distance function. This is r, and f of xy, which is x2 plus y2 is r2. So this function is very, very cherished, special, canonical function. It's a very, very important function. It's a square of the distance. I mean, that's absolutely important function. So if we didn't have this sort of simple simplification right at the beginning, we wouldn't be able to bypass chain rule. We have to go through chain rule. Any questions? There's nothing in the chat, so no. So I think we have about 4 minutes left, but we are okay. So we are in good shape now to call it off, call it a day for us at least. And so I see you on Monday, guys. Have a wonderful weekend and enjoy this amazing day. So it's a beautiful day today.
Oh, Professor, just a second. I think the chat is still disabled.
The chat is still disabled, really? But I have chat here.
Yeah, like I can click on it, but then it just says chat disabled.
That's so funny. So let me just stop the video and then we discuss. So pause.